right, good morning, everyone. How is everybody doing this morning? I have one thumbs up, that's great. It's 9:30, it's not that early. It's not too terrible. Two thumbs up, yes, yes, excellent. Oh, back down to one. Oh, so sad. Stormy in Kelowna, yeah, it was crazy. We lost power in Penticton this morning, which is kind of weird. Yeah, I just found it's been really windy and yeah, a little, even last night it was kind of crazy, right? Oh, righty. So, a couple housekeeping things. I've tried to get back to most of you that have sent me an email already about the cumulative lesson plan. So, those of you that have emailed and chosen a topic that somebody else hasn't picked, I have updated all of that information so I can show you just how that looks. I think I have it in here. Let's see. It's a little bit weird. I can't quite get what I need to on my computer for you guys yet. I'm still learning how to do the whole online Microsoft thing. I find that kind of annoying. Okay, this should work. So if you go in and download that Word document on our Moodle page, I've started just crossing off the topics that other students have chosen. So those of you that have chosen something, I've tried to kind of cross some stuff off for you so that another student looking at this list wouldn't be able to take the same topic. So for those of you that still haven't had a chance to take a look, go ahead, look at the curriculum, look at some of these topics and try to pick something that someone hasn't taken that is roughly in the neighborhood of something that you might want to do. All right, other than that, let's jump into a quick little recap of what we saw yesterday. So we were looking specifically at logic and looking at statements and trying to kind of get a sense for what a statement is. So we decided that, well, we wanted to work with sentences that actually we were able to assign a truth value to. That's typically what we would like to do in mathematics. So we want to kind of weed out certain statements that have subjectivity or certain statements that might be true and false at the same time. They're kind of like these really awkward statements. So most of the statements we looked at, most of the sentences we looked at yesterday were indeed statements. They had a truth value. They were either true or false. We also looked at some kind of weird cases where we could assume that it's either true or false, but not both at the same time. So this weird Terry Fox example, as well as this mathematical sentence, x plus 5 is equal to 8. So a couple examples where where sometimes the statement is true, sometimes the statement is false, but it's always a statement because it only carries one of those truth values at a time. Now, we looked at those kind of weird examples at the end of class, like it's hot outside. The word hot is a little bit subjective here, so we weren't really able to do any work with this particular sentence. And then we had that like kind of mind-numbing example, this sentence is false, where it was actually true and false at the same time, which I find a little bit weird. So we're not going to work with those kinds of things because they're kind of weird. Okay, so what I would like to do to start off today is let's work on negating a statement. So sometimes it's possible to be given a statement, we know what the truth value is, but we're interested in converting that into another statement that has the opposite truth value. And in the simplest sense, the easiest way to take one of these simple statements that we're working with and negate them is just to add the word not in. So for example, if we have something like the ball is round, maybe you guys can toss up into the chat, how would I negate this particular sentence? This is not a trick question, I promise. There are no trick questions, no trick questions at 9:36 in the morning. And the ball is not round, yeah. So really the only difference between the negation and the original statement is this extra word not. And that's typically true for these kind of simple statements that are non-mathematical kinds of statements. So mathematical statements, we will take a look at those and figure out how to negate those things. But typically the easiest way to negate is just to add the word not. And mathematicians have basically just created a notation for the word not. It's a slash. So if we're looking at something like, I don't know, something like this, we're going to try to negate 2 plus 7 equals 3. Obviously not true. So what I want to do is I want to negate this to make a truthful sentence or a truthful statement. And the easiest way to do that is to tackle what we call the relation of this statement, which is the equal sign. So get out, I know it's a little bit, we're a little bit of ways from Halloween, but get out your Friday the 13th gear and get your slashing gear ready. We're just going to change our equal sign into a not equal sign by adding a slash. Okay, and notice that I'm not changing the subjects of this statement. I don't want to write something like 2 plus 7 is equal to 9, which is truthful. But if I change that 3 to a 9, I've changed the subjects of this sentence. So I'm not really talking about the same stuff anymore. So changing this to 2 plus 7 is equal to 9 would be like going back to our first statement, the ball is round, and saying something like, the cell phone is round. And it's like, well, who cares? Originally, I was talking about the ball and its property of being round. I don't want to talk about a cell phone, right? So in order to negate the statement, we want to keep the same subjects and try to figure out how to add that not in. So maybe let's just write like a little note here for ourselves. This is a nice little note, I think, to have in for your reference. So we don't. So how would we say this? So like effectively, we're talking about something else. Effectively, we've created a brand new statement that really isn't connected to that original statement that we were talking about. Does that make sense? Let me know if you have any questions about that, or if you're happy with that and that kind of makes sense for you. And then if that makes sense, just kind of throw it up in the chat or give me a thumbs up or something like that. If those make sense, we're going to work with some more challenging relations for our mathematical sentences. So Vincent, you said it exactly perfectly. The whole point of negating a math statement is to leave the subjects the same and change the relation. Yes. Um, and even in a regular statement, you can kind of think the same way. The ball is round, so kind of the subject is the ball, the property of interest is the roundness of the ball, and the relationship is it being round, right? The verb here is the relation. So we're changing that verb from is to is not and keeping the subject and that property the same. Yeah, so I think you said it exactly perfectly in the chat. Okay, so equals, of course, and not equals are types of very common relations that you're going to see and use in your mathematics career. And other ones that you guys are probably going to commonly see are the greater than or less than variants as well. So, I mean, let's put our first two that we've worked with already. So the first one is an equals. Second one is a not equals. And then we have some of these variants. So just wanted to refresh your memory on some of these other variants. So we have the less than symbol. We have the less than or equal to symbol. And then we have the greater than variants as well. So greater than and greater than or equal to. Now, it turns out that these four relations can get paired up in such a way that they're opposites of each other. So in other words, if I start thinking about taking my less than symbol and trying to negate that relationship, so if we try to negate this, we'd get something like, we would change it from less than to not less than. And what I'm trying to tell you is that this is actually equal to another symbol that's up here. And it's, I think, a common misconception to convert not less than into greater than. But the actual opposite of this one is greater than or equal to. So does that make sense what I'm trying to say? So if I'm trying to negate a less than or greater than, I put a slash there and I get not less than, for example, but that's actually equivalent to one of these other relationships that we have. So it's kind of like simplifying the relation. We kind of simplify it to a greater than or equal to symbol instead. This has something to do with the number line, by the way. So if we're working on the number line and we're working with a relationship like x is less than 3, for example, so we have the number 3 here, and we're curious about all of the numbers that are less than 3, we could find the opposite of this region by doing something like this, by shading in this circle, shading in the upper region, and noticing that we get, oh, x is greater than or equal to 3 as that new shaded in region. So the opposite of less than 3 ends up being greater than or equal to 3. Hopefully that makes sense. So this is kind of like just a little example of how that's all kind of connected together via the number line. That's a little visual representation for you. But let's work on a couple more examples with these kind of weirder relations. Actually, maybe I'll just scroll up. I'll give us a little bit of room in between. Yeah, so here are the 4 we're going to try to negate. I think that will get us kind of to the end of the lesson here on statements, and then we're going to start into a kind of a new little lesson here. But yeah, I think, is it Pankaj has given us a solution for number 1. So if we want to negate this first statement, x is less than or equal to 0, we want to change this to x is greater than 0. So in green, we'll do the negations. What about for number 2? Now, I don't really care whether or not it's true or false. I just want to find the negation of the thing. So obviously 4 is not less than 3. So this is a case where maybe I want to negate this to get a truthful statement. And I can negate this by trying to find the opposite relation. Okay, so the negation here, based on what I have, based on the relation that I have between the 4 and the 3, would be 4 is greater than or equal to 3. Right, so I go find that opposite relation, then the less than, which is greater than or equal to, toss that in there, that's my negation. All right, for number 3, we can leave our subjects as they are, and then we have to find the opposite relation for greater than or equal to, and that's going to be our less than symbol. Yeah, you got it. You got it. just as I finished it up there. Perfect. Perfect. Okay, and one last example similar to kind of what we've been doing. If y is greater than x, then the opposite or the negation of that statement would be y is less than or equal to x. So there you go. There's a little lowdown on kind of basic statements, how we try to negate these basic statements, and working a little bit more with mathematical statements, which is probably going to be a lot of the focus of our course here, is these mathematical statements. Did you guys have any questions before we move into our next lesson inside of logic, which is working with quantifiers? And it may not be, it could be a question about the lesson, it could be a question about something else, but we have a little bit of kind of time now if you have some questions about anything. So just kind of let me know. Can I explain number 1 from this particular example? Sure. I think the easiest way to explain mathematical relationships like this, especially when an x is involved, is to take a look at what this might look like on the number line. Okay, so let's take our number line. Let's put in the number 0 because that's the subject that we're kind of working with here. And what we want to do is we'd like to shade the region that is less than or equal to 0. Okay, so this region over here is less than 0. And if I shade in this actual dot here, then that shades in the equals to portion. So in red, we have x is less than or equal to 0. If I want to negate this statement, I want to find the opposite region on the number line. And the opposite region on the number line is going to be everything up here. So everything bigger than 0. Okay, notice that I actually don't want to include 0 because 0 has already been included in the red portion. So if you remember some work with number lines, this would be an open circle at 0 technically, and we want all of the numbers that are bigger than 0. So that's our negation. Yeah, no worries. Now, I do believe that you all have the ability to annotate my screen as well. So you can take some time as I'm tossing in another lesson here for us, if you would like, just to kind of play around with the annotation. That way, if there's something that I'm kind of chatting away and there's something on the screen that you guys want to like kind of point out to me, or there's maybe a mistake, or you're like, explain this, you should be able to like annotate the screen and actually let me know. Yeah, so you should be able to kind of point at stuff or like move stuff around. Chapter 1. Okay, how do I want to do this? Can I rename this? Let's go. Kind of weird because it doesn't show up nicely over here. Bummer. Okay, anyway. We're going to do a little lesson on what we call quantifiers, because quantifiers do come up quite a bit in mathematical sentences. So I'd like you to know what they are and have the ability to do some work with quantifiers. So the first main quantifier we would like to talk about is called an existential quantifier. And because it's kind of annoying to write existential quantifier all the time, I'm going to sometimes short form that as capital E, capital Q. So we'll call it an EQ sometimes in short form, just so we don't have to write it out all the time. And an existential quantifier is something, some kind of wording that lets us know that one of the things that we're talking about has a property. It's hard to explain these things in words, but I'll do what I can. Okay, so So if I have a set of objects and I want to make some kind of statement about one or maybe several of those objects, as long as I don't want to talk about all of those objects, we use what's called an existential quantifier. So let's maybe take an example. So let's work with a set of shapes. So I'm going to draw some shapes here in red. Oh, can Brian draw some kind of fancy shape today? Can he do? Hey, not bad. Okay, so we have a set of 4 shapes. We have a triangle, a square, a rectangle, and what is that? An octagon? 1, 2, 3, 4, 5, 6, 7, 8. Stop sign. And I'm going to make a statement about this set of objects where I talk about, or maybe you guys can do this. Can you make a statement that refers to one or several of these objects without referring to all of the objects? So I'll start and then see if you can kind of follow my lead to make potentially some more statements. What is the width of the rectangle and square? Whatever you want it to be, Ryan. 100 meters, I don't care. I guess as long as all the things that have like the little ticks are the same. What's your favorite number? Do you have a favorite number? Oh, that's your answer. Gotcha. Yes, you're asking a question involving 2 of the subjects, which is the square, or 2 of the objects, square and the rectangle. Gotcha. Let's try to instead of making a question, let's try to the 2 of the objects have 4 sides. I like that. Yes. So I'm going to try to take that idea that's on our screen right now and try to rewrite it in a way so it's not a question and more of a statement. Okay. So let's say something like, there are 2 shapes that have 4 sides. Right, so we're kind of changing it from a question. I don't want to ask a question. I want to actually make a definitive statement, something that I can argue whether or not it's true or false. So I don't want to ask a question. I want to make a sentence. And I want to talk about the shapes. So yeah, 2 of our shapes have 4 sides. Perfect. There is 1 shape with 4 equal sides. Love it. To whomever has put the blue text on the screen, do you mind erasing that blue text? Thank you. One object has 3 equal sides. Perfect, yeah. And I don't know if it's equal, but we'll pretend they're equal. Just for you. Just for you, Chloe. We'll make that a nice equilateral triangle. Kind of looks like I just put a face on the triangle, but we'll put little tick marks there to let you know that those are equal sides. One object, yeah, at least one object has 8 sides, sure. At least one object has 6 equal sides. Yeah, if we agree that that octagon has all equal sides, yeah, then at least one shape is going to have 6 equal sides too. So those are some examples of what we call existential quantifier statements. Statements where we're talking about some of the objects inside of our set, but not necessarily all of the objects inside of our set. And what I want you to notice is some of the terminology that we get based on these statements that we've created. So it's very common to use the phrase at least one, right? It's very common to use the phrase there is or there are. So these are common phrases that I want you to know are existential quantifier phrases. So I think those are the most common. Just let me double check my notes here and make sure I haven't accidentally missed one. No, those are typically the three most common ones that we're going to see. And our leading questions for the time being are going to be, how do I show that, one of these statements involving an existential quantifier is true, or how do I show that it's false? So if we just kind of zoom out a little bit and take a look at our set of shapes and some of the statements that we came up with for our set of shapes, we actually, well, I think all of the ones that I wrote down were all truthful, right? So all of these statements were true. How did we know that these statements were true? So in other words, if I wanted to, yeah, exactly. I guess that's the easiest way to say it, Alyssa, is like, I can just go over to this set of shapes and check to see if the thing that I'm talking about is there. So exactly. So all you really need to do to show that an existential quantifier statement is truthful is to look at all of your objects and just check to see if at least one of them has that property that you're talking about, okay? Okay, hopefully that makes sense. You just kind of go through that set or that set of objects, try to find at least one of those objects that has the property that you're interested in. So let's see. Yeah, so you got it, Ryan. So that's going to be the follow-up to this is like, how do I show that it's false? I'd have to go through all of the things, show that none of the things have the property. Yeah, you got it. Look at you. You guys are being so logical today. I love it. Isn't it nice when things make sense? Okay, so let's try to create a statement and try to show the process we might go through to figure out if something is true. So show that. So let's show that the statement is true. That's an interesting question. I'm trying to think. One is a true claim and one is a false claim. I think we'll talk about that in the next lesson, which is on compound statements. So hold on to that question for a hot minute. Because I think in order to combine stuff together, you're going to need to do something kind of specific. You're going to need to probably use the word and to connect those things, or use the word or to connect those things. So hold on to that for a second, and I think we will talk about that. You're jumping to the good stuff. Okay, so here's our statement. Inside the set of positive numbers, there is an even number. And let's go positive. I guess positive whole numbers might make more sense here. Let's just keep it nice and easy. So if you want to just add this like little addition, let's just keep it nice and basic. We're going to work with the counting numbers like 1, 2, 3, 4, 5. So we're actually going to just jot down that set for our reference. Okay, so we're working with 1, 2, 3, 4, 5, etc. So, the numbers we would start to introduce our students to in kindergarten and grade 1. Okay, is it true that inside of this set, there is an even number? Is that true? How do you know that's true? The answer is yes, I totally agree with you. How do you know that that statement is true? Give me a concrete example. Yes, so I mean, I can look at this set. I know that this statement is true. And I think Alyssa has given us a potential solution here. I can look at this set. The number 2 is even. I know 2 is an even number. I know 4 is an even number. So I can actually go in and find a particular example and use that example to prove this statement to be true. Okay, we know the statement is true since 2 is even. Okay, so 2 is a number that satisfies the property that we're looking at, which is being an even number. So remember, even number is something that is nice and evenly divisible by 2 without any remainder. So 4 is another example. I don't have to choose the number 2. That just happens to be the first one that we find. 4 is evenly divisible by 2. 4 divided by 2 is 2. 6 is another possibility. And actually, every other number is a possible example that I could use to show that this statement is true. I could use the number 12 if I really wanted to, but why would I go all the way over to 12 when 2 is the very first one that I find? So I guess just kind of going back to what we were talking about, we look at the set, we try to find potentially the easiest example and use that to show that this statement is true. All right, so time to put on your thinking caps. The next statement is there is a state in the United States of America beginning with the letter V. And yes, we have potential solutions happening via chat. So it's totally true. So Ryan has given an example and Vincent gave us an example in the chat as well. So yeah, so I know it's true because I can go and find a state beginning with the letter V. Virginia or Vermont are both possible ways to argue that this statement is true. Okay, Virginia, also another possible answer. Cool. So that's kind of the idea with the existential quantifier. Essentially, we look at the objects, we try to find one of the things that has the property we're looking for. If we can find it, we know it's true. And kind of tying back into what Ryan was asking earlier, if I want to show that one of these things is false, I actually need to go through all of the objects one by one and figure out whether or not they have the property we're looking at. Okay, so here's kind of part 2 to this question. Okay, so I'll say that out loud to see if that makes sense in your head. If I have an existential quantifier, something that says like there exists or there is a thing, right, in this set that has this property. What I want to do to argue that this is false is actually look at all of those objects inside the set, go through them one by one, and make sure that none of them have the property. If I can do that, then I can argue that this statement is false. So that's kind of the method of attack. Notice that this is hard. So this is a really hard thing to do if I have a really big set of objects. So if you're trying to make your students like kind of work with, uh, you're not really going to be talking about quantifiers or existential quantifiers, but maybe you want them to look inside of the set of shapes and figure out if there's a shape that doesn't have any straight edges, right? And then in which case they have to go through all of the things one, but try not to make that set too big, right? Try to make it manageable for them so they're not looking at 15 different shapes and having to go through all of those 15 objects, try to keep it nice and small. Let's see, let's work on an example. Okay, let's get a little algebraic on us today. We're going to show that the following statement is false. We have the statement, there is a real number satisfying x squared plus 1 is equal to 0. Okay, so when algebra gets involved, I sometimes get a little bit nervous that students get a little hesitant to start thinking about these things. So let's kind of break this down a little bit and just start working with some of the terminology that we know. We want to try to figure out what kind of objects we're working with. In this case, we're working with real numbers. So real numbers are all of our whole numbers, all of our integers, all of our decimal numbers and fractions. So all of those kinds of numbers are the objects we're working with. Notice that this set is really big. It's pretty fucking big. In fact, it's infinitely big. So yes, we are involving integers as well as a bunch of other stuff. The property that we're curious about is whether or not I can take that number, square it, add 1 to it to get a solution that's equal to 0. Okay, so can I take a number, square it, add 1 to it, and get a value that's equal to 0? That's the property we're curious about. Now, if I want to show this statement is false, I need to go through every single one of my numbers and kind of convince myself that none of them satisfy this property. Okay, so that's kind of our plan of attack. We want to convince ourselves that there really aren't any numbers that are going to satisfy this equation. Now, we can do this just by kind of talking back and forth, or we can actually work with the algebra a little bit, maybe kind of bouncing over to our calculator if we need to. But I'm hoping that you remember at least some of the operations that we need. So let's work with the algebra bit first and see if we can convince ourselves using algebra. So if a number had to satisfy this property, then maybe you could agree with me that x squared would have to be equal to -1. Okay, so make sure that makes sense. If a number satisfies x squared plus 1 is 0, then x squared has to be -1. Now, in order to remove a perfect square like this, we take something that's called the square root. So what I could do is I could take this algebraic statement, which I have, and I could apply the square root function to both sides. And that's going to give us x on the left-hand side. So the square root and the square, if you remember from middle school, those will cancel each other out. And I'm going to be left with x is equal to the square root of -1. And that's not a thing that we really have ever worked with before in like middle school or high school, right? The square root of -1, that's not a real number at all. I can't take the square root of a negative number, at least not over the real numbers. I don't want to say it doesn't exist. I just want to say it's not a real number. So in other words, if I tried to solve this in an algebraic kind of way, I get that there's a solution, but the solution is square root -1, which isn't a real number. So it's not a number inside of the set that we're working with. So kind of take a moment just to take a look at that one more time. See if the algebraic approach makes sense. If you have any questions, you can ask those questions now. Okay, so yeah, it's a good question. Why is it not a real number? This is actually what we call a complex number. And it has something to do with this right here. It has something to do with this. So this is kind of the other way that you can try to argue to yourself that this can't happen. It's not possible for us to square a number and get -1. Every time I square a number, it's actually a positive number, right? If I do a positive times a positive, I get a positive. And if I do a negative times a negative, I also get a positive result. So no number squared can actually ever equal -1. No real number anyway. Right? So the idea is if I try to take any number that could be positive or negative and I square it, I always end up getting a positive result. So it's not possible for us to ever get -1 as a result when I square something using my calculator, for instance. So that's another way you can kind of argue this to yourself. Is that enough? Does that make sense, Ryan? Yeah, no worries. Yeah, it always gets a little tricky when you have these algebraic expressions involved, right? Okay, so good times. Logic is fun because we get to have these outrageous sentences and we get to have debates with each other about whether or not we think they're true or false. So let's make an outrageous sentence, and that outrageous sentence is there exists a bear who can balance on a basketball. I don't know if that's true or false. I have no idea. But what I want to do is I want to think about how I might convince myself that this is false. So what would I have to do in order to argue somebody that this is false, right? So somebody walks up to you and says, there exists a bear that can balance on a basketball. And in your brain, you're going to be like, how could I prove to them that that may not be true? What would I have to do? And make specific reference to the set and property that we're working with. So after you've finished kind of copying this down, let's try to figure out what the objects are that we're working with and what the special property is that we're working with. Because that'll make this a little bit easier for us to discuss. So if anyone has some ideas on what the property is or what they think the set of objects are, throw that up in the chat. Yeah, I'm going to run with the bear. So let's think about a bear as the set of objects. So we're going to look at the set of all bears. So bears are going to be our set. And yes, exactly. The balancing on the basketball is actually in the property that we're curious about. Okay, and that's helpful because now I have some kind of reference. Now, if we kind of scroll back to maybe one of our easier examples, when we were looking at, say, this set of numbers, we listed the set and we started going through one by one, trying to find a number that had the property, right? So that's kind of our method of attack for existential quantifiers. We look at our set, which in our case is the set of all bears, and we go through one by one, trying to find a bear that has the property in question. So if I want to show that this is false, I look at every single possible bear, make sure that none of them can balance on a basketball. That would be enough to show that this is a false statement. So I'll write that down and see if that makes sense logically to you. So let's do that in green. Uh-oh, bear on a ball JPEG. What is this? I don't know. Is this a virus? I really hope it's a meme, Chris. Tell me it's a meme. Oh, goodness. Oh, Alyssa, yeah, Alyssa, you did it. Okay, so here's what Chris sent in the chat, which I think is this is a good, kind of fun thing for us to discuss. Here's a bear balancing on something, but it's not technically a basketball. So you're right. So, I mean, this is pretty close. It's a bear that can balance on something, but since it's not a basketball, it doesn't quite fit the bill, right? It doesn't quite work with the subjects we're working with. If it was just proving that a bear can balance on an object, yeah, this would show that that is a truthful statement. Maybe he's too heavy for the ball. I love it. I just love that you're able to find, yeah, I think it's fun that you're able to find a bear that balanced on something. I thought that was fun. But anyway, the point here really is not to, we can't really prove that this is false, I think, right? Like there's a possibility that there could be a bear out there that can balance on a basketball. This would be a hard thing to do. There's lots of bears in the world. To actually have to go through bear by bear and actually figure out if each one can balance on a basketball, that would take a long time. It would be really hard to show that this is a false statement. And it's probably more likely that we can find a bear that actually can balance on a basketball. It's probably a truthful statement. I mean, there are circuses out there, right? I mean, if a polar bear can balance on a rain barrel, there must be a black bear that can balance on a basketball, right? There's gotta be something out there. So there you go. There's a little lowdown of existential quantifiers, how to show that they are truthful or false. We have class tomorrow, right? So let's see. What do I want to do tomorrow? What do I want to do for tomorrow? I would like to post up. I think what we're going to do for tomorrow is I'm going to post up a pre-recorded lesson tomorrow, but it's not going to be in logic because I think logic is kind of one of those. Oh yeah, Friday. Sorry. Yeah, I meant Friday. Thank you. So I was starting to get nervous. I was like, we have class tomorrow. Oh my God, I need to do stuff. So that's good. I have an extra day now. Yeah. So I'll post up a recorded lesson on Friday. The recorded lesson on Friday, what I'm going to do is I'm going to go into the BC curriculum. I'm going to grab one of the content pieces there and try to develop a lesson plan with you. So I'll kind of show you kind of the nuts and bolts of how to use that template to design a lesson. So I think that's going to be the pre-recorded lesson for Friday. And then what we'll do is we'll pick up with quantifiers in class next week on Monday. Our Friday classes, yeah, I think I'm going to try to make Friday classes recorded so that you can kind of do that class whenever you'd like to over the weekend. And I try to make those ones a little bit shorter typically, and involve topics that are kind of more maybe theory based, or maybe a couple examples that I find to be rather straightforward. So I'll try not to do any hard topics on those Friday pre-recorded lessons. But yeah, we'll try to make Friday pre-recorded so that you have a little bit of flexibility to do that class when you would like on the weekend. So I am going to end class here. I know we technically go to 10:50, but I usually like to end the class just a little bit early in case students do have questions about stuff. So if you have any questions about any of the content covered today or last class, or you have any questions about some of the assessments, now is your time to ask those questions. If you don't have any questions, that's it for class today. You guys can mosey on out to your next class or back to bed if you want to have a nap, whatever. The world is your oyster now, right? You can do whatever you want. You are very welcome, everyone. Thank you for tuning in and talking about bears balancing on things. It's always a pleasure to talk about balancing bears. All good, Laura. I'm just happy that you're able to make it. Just don't be late when you're actually teaching. What constitutes a real number? So a real number is we'll talk about this, is technically the set of all rational numbers and all irrational numbers. So right now we don't quite have enough to be able to talk about real numbers, but real numbers, if you want to do a little bit of digging, are the rational numbers plus what we call the irrational numbers. So that's the best way to define a real number. Do we have an end of? The first end of chapter assessment will come after we deal with sets. So we're not through this first kind of chapter yet. I still want to do a little bit more with logic. Maybe we'll have an assessment after the logic chapter is done, or I might push it a little bit further, and we'll maybe do a little bit of work with sets as well before we have our assessment. So I will let you know when that first assessment happens. So nothing quite yet. We'll probably be a couple weeks out on that first assessment yet. So Chloe, for the negation part, is the purpose of them simply to show the opposite? Yeah, that's a nice way to think about the negation. The negation is essentially taking the statement, leaving the subjects the same, and kind of formulating the opposite of that statement. Yeah, I think that's a nice way to think about negation. Especially when we're thinking about like mathematical statements, definitely. A little bit harder to think about the opposite of a regular statement, but hopefully that makes sense. So is there a document available with the criteria for the cumulative unit plan? Available with the criteria. So you're going to be looking for the rubric, and I'm still working on one of the rubrics. I have one of the rubrics done. I have the kind of per lesson plan rubrics done, but I'm still working on the overall cumulative rubric. So yes, that will be coming shortly. Let me actually just check. I'm gonna pop into Moodle just to see. Okay, why are you not? There we go. Let's pop into Moodle. Let's see what I actually have. So I have the lesson. Oh, I see. I have the lesson plan. Yeah, I don't have any of the rubrics up. So yeah, I will get. I do have the lesson plan rubric done. So I will post that one, and then I still need to get kind of the overall kind of formatting and kind of big cumulative rubric done. But I should have that done hopefully after the weekend. So they're coming shortly, coming soon to a Moodle near you. Ryan, it's going to be a mixture of both. So I think when it comes to this first assessment with logic and set theory, Probably what I'm going to favor doing for the logic portion of the assessment is have like a little quiz where you just kind of like type your answers into Moodle. And I think for the set theory portion, we might try to do a lesson plan to get you guys kind of used to creating a lesson plan. We'll try to connect like set theory to something from like the grade 2 or grade 3 curriculum, something kind of nice and straightforward and simplistic. So I think that's what we're looking for the first assessment, but they are going to vary, I think, from chapter to chapter. I tried to keep it very vague so that we had a little bit of flexibility to have different kinds of assessments, because I think having tests all the time is kind of boring, especially when like, I mean, yeah, tests are good. They're good as assessment tools to let you know how your students are doing. But like when it comes to actual marks for you guys that are going into teaching, I think it makes more sense to do more project-based things to get you actually involved with a curriculum. So I'm going to try to favor that kind of stuff over tests for the most part. All right, so not seeing any other major questions, I am going to...
Can I jump in and ask a question?
Yes, you may, of course you can. What would you like to do?
Well, this is very elementary. I'm not very good at this logic. So we went through this statement, and today we talked about EQ.
Yes.
EQ is the component of the statements. Am I correct?
Yes, so it's a
And
statement
EQ,
that has one of these special phrases.
and EQ can break into property and set of objects.
So every statement you can do that for. I find it helpful when we're working with quantifiers.
So
yes, you're talking about
exactly,
like some of this down here, right? The set of objects and the property. You can do this for every statement. So even if we go back to our first lesson and we look at some of our statements, like x plus 5 equals to 8. Well, maybe that's not a good example. Canada has only 5 provinces, right? So our set of objects here is the provinces in Canada, and the property is having only 5 or something, right? So I think you can kind of do this for every statement, but I do find it most beneficial when working with quantifiers.
Okay.
Because we often need to know what objects we want to work with, and we often need to know what kind of property we're interested in.
Okay, thank you.
Yeah, you're welcome. Travis, there's no rush on getting a topic picked. The only kind of rush would be to pick a topic that you want to do before other students. The cumulative lesson plan, the draft of that's not going to be due till after reading week anyway. So we're a little ways out on requiring that topic to be picked, at least a couple weeks. You have a little bit of time. There's no immediate rush. Yeah, you're welcome. All right, guys, I have to run to my next class, so I'm going to go ahead. I'm going to end off our share here, and we will get all of this posted up for you as soon as we can.